Yes, so welcome everybody, and welcome Mary Hall. We are super happy that you found the time to join our seminar here. I mean, Mary is a true giant in compilers. She's very well known through the SUEF compiler infrastructure. And now Nikolai will actually introduce her more formally with more technical background. So thank you so much, Mary, for joining us.
Thank you. Thank you, Torsten. And thank you again, Mary. I just want to echo what Torsten said. And Mary is a professor and director of the School of Computing at the University of Utah, where, as Torsten said, she works on compilers and many other relevant areas to all of our interests. She received her PhD in computer science from Rice University, is a IEEE Fellow, an ACM Distinguished Scientist, a member of the Computing Research Association Board of Directors, has won numerous awards, published many top conference papers, don't have time to go into them all. She also actively participates in mentoring and outreach programs for women and underrepresented groups in computer science. And with that, I'll let Mary take it away. Thank you again.
Thank you, Torsten and Nikolai, and I am really pleased to have this opportunity to virtually visit you. I physically visited ETH a couple of years ago, and I'm sure I met some of you on that visit, and some of the work that I'm going to talk about today was going on at that time, and some of it has happened since. The focus, so as the intro said, I work on compiler problems in high performance computing. And the focus of my talk today is how we can think about optimizing computation and data layout jointly to optimize data movement. This is joint work with a bunch of people. I'm going to focus most of the talk on the brick data layout and how it's used in Stencils, but I also am doing a bunch of work with a different group of people on sparse tensor computations, and I'm going to just kind of tease that a little bit. We should have an archive paper out. We submitted a paper last night that should have an archive paper coming soon, so you can read about it a little bit more. And this work was supported in part by the Exascale Computing Project and also by the National Science Foundation. So since there are students in the audience, I'm going to give a little tiny history lesson to talk about the role of programming, sort of hinting at the role of programming systems in the evolution of architecture. So I'm going to talk about computing eras and where we are now. So the first piece of context, if you haven't heard of Bell's law, is that a new computer class forms roughly each decade, and it establishes a new industry. And the new computer class is always cheaper, smaller, or more capable than what came before it. So the way this cycle works is, more or less once a decade, some new architecture comes along, and it's in response to whatever technology trends are going on. And then new programming systems are designed for that new architecture, and they have to do two things. One is exploit whatever is really great about the architecture, and the other is hide the complexity of what's really hard about the architecture. And so then there's a period of assessment. How well is this working? Usually the answer is not all that well. And so then there's then we enter a new round to try to address, whatever changes have happened during that decade. So you observe and you predict what's coming next. And so I started graduate school at the end of the 1980s. And so at that time, everything was about maximizing the flops that you could get out of an architecture and out of a program. And the architectures at the time were vector supercomputers like the Cray 1. And the programming systems at the time were vectorizing compilers. In the 90s, the observation of the memory wall, became a really dominant thing. The memories are optimized for density and processors are optimized for speed. And so there became a growing gap And now we needed to worry about caches, and the programming systems were focused on locality optimization. In the 2000s, we reached the end of Dennard scaling. And so that led to, multi-cores everywhere, low power optimization, vector units in every microprocessor. And the programming systems are really focused on exploiting parallelism for the most part in various forms. The 2010s were sort of a reaction. I like to think of it as a reaction period where, gosh, all this parallel computing, we're not taking advantage of it. We have it, but we don't know how to take advantage of it. The programming problems are really hard. The software is limited in what it can do. And this is when, well, heading into the the late 2000s era, that's when my group started looking at automatic performance tuning or auto tuning, because we observed that compilers are really good at generating high quality code, but really bad at deciding what set of transformations to apply to get that code in, in all contexts. And so, so we started also seeing things like domain specific frameworks, and so that you could specialize instead of trying to do some general purpose solution. And so now we're in this era where data movement is the dominant cost, both in terms of performance and energy. And this graph here from the Kogi and Schaaf paper was sort of speculating exascale architectures. And it basically shows that the power and the energy and also the performance as a consequence of computation is going to, the data movement is going to be dominant, and it's going to go up by orders of magnitude as you move the data farther and farther away from where it needs to be computed. And so the message here is that if data movement is everything, then we can no longer afford to waste time or energy on unnecessary data movement. And we really have to just focus our optimization efforts on that. And so this talk is about how to reduce and accelerate data movement. So not just reduce it, but when we have to do it, which we do have to move data, to do computations, that we do it faster. If you look at the way in which people who write software or build compilers reduce data movement, and I'm going to focus right now on vertical data movement, which passes through the memory hierarchy. So the common optimization, well, let me just say that. So we want to do locality optimization, and that is accessing the same or nearby data in fast memory. So we want to take a program that maybe is not exploiting locality and figure out how to modify it to get it to use fast memory. So the typical way to do this is to reorder a computation such that we change its memory access pattern. We do the computation in a different order, and that changes its memory access pattern. And we call these in compiler literature, we call these reordering transformations. And the most common one in the literature is tiling or blocking, where you're operating on a small window of data, a small footprint of data that fits in some part of the memory hierarchy. And you do all the computations, you reuse data from that small window, and then you move on to the next window. So these are reordering computations, but there's another thing you can do, which is reorder the way the data is laid out in memory. And so this could give us, this is a different way to achieve a desirable memory access pattern. So I made the first observation that hardware designers are really good at designing hardware features that can move a chunk of contiguous data from some large slow memory to some small fast memory. And so we have lots of features that exploit this sort of property, and they range from DRAM page mode access to TLBs, operating at a virtual memory page, so different scales. And so it's not only does this help, so we can take advantage of this moving data from contiguous data. We can take advantage of it at all scales of the architecture. So what if we organize the data to take advantage of the fact that the hardware is good at making this fast? And because we do have to move some data, we every computation's data needs to be moved at least once. So so this is making the requisite data movement more efficient. Okay, so the theme of the talk is that we need to co-optimize the computation and the data layout, and both the data layout and the data representation, and do that in an architecture specific way. And so, and that way the code can be generated for different target architectures, because one of the things that's happening in this era of computing is we're getting a lot of different kinds of architectures thrown at us that look very different and that require very different code. So what does this really mean? It means that implicit or explicit data layout is exposed to optimization and code generation. And that set of layouts need to be richer than traditional compilers. Because, for example, in a traditional compiler, we know that an array or a tensor is laid out, if it's C code in row major order. So we know how to map from a location to an address. But that's a very specific layout. And when people do tiling optimizations, they're taking advantage of knowing that layout and favoring a particular dimension as a consequence. So we want a richer set of layouts, and we want code generators that understand that layout and can generate correct code for it. And then this can be tailored to different architectures so that we get performance portability, so that we can have high performance across different platforms where the code that gets generated may look very different. Okay, so I'm going to describe for this part of the talk a domain-specific framework we built for Stencil Computations, where data layout is the dominant focus of the system. So stencils solve partial differential equation. The outputs are computed from neighbors in a multidimensional space, and each input is typically multiplied by a coefficient. So these pictures on the right show different kinds of three-dimensional stencils. The first one is a 13-point star-shaped stencil. The middle one is a 27-point block-shaped stencil, and then the bottom one is a 125-point block-shaped stencil. And so these different kinds of stencils have very different data movement and memory performance. So this access pattern also rises in image processing and the all popular convolutions as well. So the number of inputs that you have in a stencil computation is related to the order of the stencil. So the low order stencils, like the 13-point or even at the top, they tend to be memory bound because you're not reusing data very much across stencil application. And you have to load a large number of inputs and do a small amount of computation, to produce an output. So the higher order stencils tend to be compute intensive, like this 125-point stencil, but they also have data movement challenges. So let's dive in a little bit and see what's going on. So the kind of data movement that arises from stencils. Here we have a 2-dimensional 13-point stencil. And the code is at the bottom of the picture on the left. So the thing you can see, this is, think about this as how the data is laid out in memory, and we do one row at a time. So the thing you can see from this picture is to get those aqua and orange points, we're accessing a lot of different address streams, and those are going to translate into different different cache lines, and in the 3D space, different pages. And so we're operating with a bunch of address streams, and some of them aren't using very many of the elements. That's going to be clear in the next slide. We also have communication related data movement, because we need to communicate a subset of a node's domain to other nodes. And we may need to do some pre-processing to send that data, because it's typically not in memory in contiguous chunks of, so we're going to have to do some kind of pre-processing. And that data movement is actually on-node data movement to support communication. So let's dive into those ideas a little bit more. So here's our different address streams sort of broken up. You can see that just for this small computation, we have 7 different address streams. And that means we're going to be pulling in 7 cache lines at least. And so we're going to end up with capacity misses in the cache and TLB, because we're pulling in, a cache line and only accessing one element of it. So we're also going to limit hardware prefetching effectiveness. And because of, if we want to do vector computation on this, we're also going to have to move data around to reorder it in registers to be able to get parallelism across stencil applications. Now, if we add many core parallelism and tiling, we're going to have more address streams, and that's going to make the problem worse. Okay, on the communication side, just to make this a little bit more concrete, we want to send data to our neighbors in all 4 directions. And the data we want to send is numbered in this picture. And so, for example, if the thing that we want to send to the west is 146, all that data has very large strides. It's not in contiguous memory if you assume row major storage. So a typical thing that's done is that data is copied into a buffer before it's sent to the neighbor to the west. And even there are some mechanisms to have an abstraction to describe that shape and have MPI library do the mapping, the buffer management. You still end up spending a lot of time doing this packing of the data, and it can be as costly as sending the data on the interconnect. And as a result, that limits strong scaling. So now I've shown you that there's a lot of data movement in stencils. And so now I'm going to tell you how we solved it with this co-optimization and architecture-specific code generation. So the idea of a brick, and I'm going to show you a picture in a minute, is it's a data layout that's designed around a unit of data and in parallel work. And we focused on the needs of stencils in this work, but I think the bricks can be very useful for other kinds of computation. So a given node has a collection of these units. And so we can aggregate at different levels to say what a thread does, what a core does, what a node does. And these collections are very flexible in how we organize them and adapt to the architecture. So this is going to do the things that I said at the beginning of the talk. It's both going to reduce the need for data movement and speed up the data movement that we have to do. And we're also going to talk about optimizations that reduce on-node data movement that's required for communication. Okay, so this is a picture that shows a collection of bricks, like the subdomain or the domain tiled into a collection of these mini subdomains. And the key idea here with the brick is that an individual brick, say 8 by 8 by 8 subdomain, is going to be stored in contiguous memory. And you can ship it around very efficiently in those hardware structures that the architects like to build for us. And because stencils reach into their neighbors, the application of a stencil is going to reach into other bricks. And so you need to think about that as you're designing which bricks are, assigned to a node or a core or thread or node. And because we now have taken this three-dimensional space and we've made it a collection of these subdomains, we need contiguous storage for the subdomains and adjacency information for the neighbors. This is just an example of writing code in the brick library, and we even have a way of generating this code if you want to make it simpler. The thing that looks different from the stencil code from a previous slide is we've added this brick index. So that says which brick you're in. If you go off the end, the code generator automatically resolves that. And this is all expressed in Python. Okay, and this is probably looks very similar. So one of the brick papers was in a session at SC with your data flow, forgetting the name off the top of my head, but your data flow system that this looks to me very similar. So this is the code generator for bricks, and it's focused on being able to optimize for different kinds of vector units and generate vector code. Like a lot of other stencil frameworks, it uses associative reordering. So the computation may be performed in a different order from what it would happen in the sequential implementation. We're identifying reuse within vectors across operations, and we're doing that with, there's a very long version of this, but we're doing that with a kind of a scatter. If you're going to reuse the vector across different computations, then you scatter it to the outputs that are going to use it. And so we exploit this reuse with a scatter when profitable, and otherwise we just use a gather that looks kind of more like and a single output comes from a collection of inputs. So this particular example is the Hypterm kernel, and it's a multi-stencil. It has a whole bunch of stencils that are calculated together. And so this is sort of some of the challenges of higher order stencils. You end up with so many inputs and so many partial computations that you fill up your register file and your performance falls apart. And so part of this is trying to figure out how many registers do I really have, because you may have to give up some reuse in order to manage the register file. And so this is a way in which the brick library can adapt, and they can make smaller bricks so that the computation is better suited to whatever computation you're doing and the size of the register file. Okay, so I mentioned this earlier, a collection of neighboring bricks is co-located for a thread or node, so we're exploiting affinity. And the indirection is going to let us not only have these, keep straight these contiguous data structures, but it's also going to allow us to have a different physical layout from the logical organization. And we're going to exploit this to also improve data movement for communication. So the point is, now I can lay out the bricks in whatever order I want and within a node. And so what we're going to do is we're going to lay out the bricks in an order that allows us to communicate most efficiently with our neighbors. And so this is, there's a whole paper on this, and I'm going to be very, very superficial, but but the key concept is that you lay out the data in the order that you want to communicate it. Then you don't have to pack it all. So we have a pack-free solution for communicating across nodes. And so now I'm going to just go over some results to show you that we really did move the needle in terms of reducing data movement. So, and these are, from last year and from a couple of years ago. So the first thing, and these are all the stencil, real world stencil kernels, and they are run on, 2 different Intel architectures, one sort of conventional, one the Knights Landing from a few years ago, and then a GPU architecture. So we compared 3 different implementations. So the baseline is a highly tuned tiled version of the code, but we rely on the compilers for the architectures to do the code generation. And the tile version is tile code, but it's using our code generator, the DAG-based code generator, but it doesn't use bricks. And then the third one, the red one, is using everything. It's using bricks, it's using the DAG-based code generation. So we can see as even on the very conventional Intel Skylake that we see a performance gain, but that gain is more significant on these other architectures. And also that the code generator does give us a win, but the brick layout is where, the combination with the brick layout is where the significant gains are. So, and so this is actually measuring data movement in different parts of the memory hierarchy for the Knights Landing and for the P100. So this is this using performance counters and in vprof in the GPU case. So we really do see a lot of reduction in data movement. And on the Knights Landing, one thing you see is these 3 things related to paging. What's going on is you have a small TLB relative to the number of cores on the Knights Landing. And so, if you're striding across pages and you have extra address streams, you're really going to pay a high penalty for that. And that's why bricks are giving such a significant win. And also seeing reduction in L2 miss, again, because of the reduction in address streams. On the GPU, we see much better register reuse. And so that's kind of showing up in these couple of metrics by virtue of the code generator. Okay, and then here's the on-node data movement for communication. So on the left, we have a comparison with YASK, which it stands for yet another stencil, I think kernel, I don't know what the K is. And it's an Intel auto-tuning for stencils code generator. So you can think of it as a state-of-the-art, and we did tune it according to the specifications of how to generate code for YASK. So that's only available in Intel platform, so we make that comparison with the KNL. And the blue is our layout optimization, and just below it is the network, the time you spend moving the data. So we're just slightly more expensive than what it takes to move it through the network, so it's because there's no packing involved in doing that communication. The top line is what people typically do, which is use MPI types to express that the way the data is laid out is different from, is not contiguous, but you just allow MPI to do the management of that reorganization and communication. And so it's quite expensive because it's still doing the data movement internally. And so the result of this is that we have much better strong scaling in using the brick layout because we don't have all this on-node costs, and we're really just paying for the network time for the most part. So on the right, on the GPU, if you want to move data between GPUs, you often end up paying some overhead by moving the data through the host. And there are a lot of improvements in communication for GPU to GPU communication, such as, for example, this CUDA-aware MPI. And also on the GPU, you have this notion of unified memory. So you can declare certain buffers to be managed by the system, and they will migrate to between host and GPU, and we can exploit that to get efficient performance. You can see the layout that's also our system performs well, whether we're using CUDA-aware or unified memory. MPI types, again, is much slower. And the layout is very close to the network time again. Okay, so it's pretty brief, but what I tried to establish in this first part of the talk is that this idea of a layout that is really good, really good at moving data around is a powerful concept and can give you good performance across different kinds of architectures. And so what I'm really interested in right now is how to generalize this. I mean, I think bricks would be very useful for domains other than stencils that are, generally block structured. But I'm also thinking about it more broadly for more irregular domains. So what do you have to do for this packed data layout to be applied to other problems? So the first thing is that the layout needs to represent a configurable unit of work for an architecture, both for data movement and for parallelism. And then you need to build a software layer for organizing and parallelizing a collection of such units and have an architecture-specific code generator. Because not everybody is going to embrace your layout, you also need a way to convert from layouts automatically, at least in parts of the computation where it makes a huge difference. So, so we've been thinking about this in the context of sparse tensors. And I took this haiku example as a particular complicated example of a data layout for sparse tensor. So, this is work by Rich Vodek and some of his former students. But the thing about haiku is it's a particular sparse tensor layout to support MTT-KRP, where you're accessing the sparse tensor. So sparse tensor has a lot of dimensions, and you're accessing it in different modes. So different dominant indices. And so what it does is it uses this block structure, so you can easily within a block access it in different modes, and it's very efficient. And it also uses Z-Morton ordering as part of its layout. So it's a really complicated thing going on. And if you want to build a code generator for this, you need an abstraction for expressing all of that. So this is kind of a challenge problem that we've been thinking about for a long time. And so the idea in sparse tensors is data layout has always been important. And if you have various libraries and some compilers have, put a lot of technology into converting layouts, or maybe they've just written, the code manually, but it is really critical, and it is not only specific to whatever the sparse tensor looks like and the computation that you're performing, but also has a lot to do, what is efficient also has a lot to do with the architecture. So it's a really good challenge problem for how data layout can be brought into the co-optimization. And so what we've been working on is composing the data layout with the computation to generate code. And one of the challenges in doing sparse tensor computation is that you may have two sparse tensors, and you need to be able to access the same corresponding locations in both the sparse tensors, and only apply an operation if both of them have the same location represented. So this is something we've been working on. As I said, we submitted a paper last night, and hopefully we'll have an archived version of it. I can talk about it. But it turns out that if you can represent the layout as, we're working in the sparse polyhedral framework. If you can represent the layout as a set of constraints, then you can compose those constraints with the computation, the constraints arising from the computation, and use that to generate the code. So I'm not going to say very much more about that. And then just a kind of a last thing, and since I'm running out of time, I'll just very briefly just make this point. Another way to reduce data movement is to make the data smaller, and that's what people are exploring a lot. And so I'm going to just review some work from a few years ago where we were looking at this just for sparse matrix vector multiply. And the key idea in this work is to use single precision for values that are well represented by single precision, and in particular things that are close to 1. So close to between 0 and 1, and positive and negative, and then use double precision for everything else. It's a very simple idea, and the thing is, it depends whether it's useful, depends on how much of your computation can be converted to single precision. And it's assuming that you wanted to do the computation in double precision. So if you can have a fair amount of your computation or your data represented in single precision, then this is a win. This is just an estimate of how big the data structure is. We have some replicated the vector X, and some you have to represent the non-zeros for both the single precision and the double precision. So it can be too big. It can be bigger than the original double precision representation. So this is looking across all the sweet sparse matrix collection. If I just use this simple idea, is it a win? Well, the answer is sometimes. And sometimes it's quite a large win. And this is on the V100, and it's for all the sparse matrices that are double precision, represented in double precision. And then the next question you would probably ask is, well, do I get the same answer? And so for the most part, the answer is yes. And so we didn't really lose a lot of digits of accuracy by doing this conversion. All right, so so I'm just gonna highlight that there's lots of different things going on in the world that are very closely related to this, and from which our work builds on, and some of it by you all. And to close, I think what we're thinking about and what we're working on is that optimizing data layout gives us performance portability by reducing and accelerating data movement. So ongoing work, we're deploying brick layout and the proto application framework for Stencils, and we're also extending it in a whole bunch of ways to, for example, support adaptive mesh refinement. We're demonstrating the generality for sparse tensors, and we're identifying opportunities not just to make the data smaller by changing its precision, but also to remove values without loss of accuracy. And we're also doing a bunch of work in the MLIR compiler, some of the sparse tensor work. We also had a workshop paper on implementing multi-dimensional transpose in MLIR, because you can use the MLIR compiler. I don't know how much you guys have looked at that. We can talk about that during questions, but it allows you different abstractions through the dialects, different abstractions of the computation that you can compose together. And so allows you a really nice mechanisms for architecture specific code generation, kind of hiding in the back end and everything else happening in the front end. So that's our future work: layout aware compiler integration. And you know, because we're supported by the XSL computing project, you know, trying to demonstrate that the code works on these new platforms. So just in closing, this is my call to the community, and you guys are probably, you know, really good people to work on these problems. Probably don't need my call, but I think it's really important that we pull these pieces together and we build compiler technology that that uses data layout and data representation as a fundamental abstraction in the code optimization. So I think that's all I have. Yeah, that was my last slide. So now I'm ready for questions. And thank you all for listening.
Thank you so much, Mary, for the wonderful talk. I definitely agree. Data movement is the bottleneck. And right just before we get to questions, I want to just give a brief shout out for anyone interested in future BCAST talks. Please check our website. We'll have a few exciting summer talks coming up on our website soon.